So, hi everyone, thanks for coming in. Hi Jason, thank you for coming in and preparing this talk for us. Jason is a former PhD student from Penn State University.
University of Pennsylvania.
University of Pennsylvania, I'm sorry, and is now a postdoc at Cornell. He works, it seems, more on the continuous time side of neural networks, which is quite different from what we normally talk about in this group. Things that might relate to biological systems, to our own brains, is now working a bit more on the controlling swarms, control theory, something like that. I hope.
many different things, yeah.
Yeah. Many continuous things. So this is going to be a really refreshing talk for us, and he's made a programming language to discuss how we might program different things inside such networks. And take it away.
Cool. Well, thank you so much for inviting me to present. As I was introduced, my name is Jason Kim, and today I'm going to tell you about a distributed neural programming language, right? You'll notice this interesting animation that's playing on the screen. And what you're looking at is a game of Pong that's been programmed into a neural network, right? This neural network is not playing a game of Pong that's run on a computer, but it's acting as the computer itself, right? So for this presentation, here's a zoomed in version of what you're looking at previously. So here is a subset of neurons. The total system has about 500 or 1,000 neurons, and each of these little circles is a neuron, and each of these lines is a connection, right? And what you're looking at is the evolution of this system as it goes forward in time, and these are how the neural states change and the corresponding representation of all of those neurons inside of its brain. Basically what I'll be telling you about is how to pick these edges in such a way to program algorithms into neural networks. So the outline for this talk, first I'll go a little bit into where I'm coming from, because it's definitely not machine learning. You can typically think about the things I like to do as engineering neural connectivity. And then I'll go into some motivation for the representation and computation in silicon and neural computers. Then I'll talk about two different programming languages for neural networks. One is a state neural programming language, and the other is a dynamic neural programming language. And then finally, I'll go a little bit into my vision for the development of neural software, a new way to think about software development. So first, a little bit of my background. And typically what I like to think about are dynamical systems. And dynamical systems just define changes in states over time, right? And very simply at the highest level, you can think about it as some equation, x dot equals f of x comma c, where c can be some inputs, maybe c are the parameters of the model, but the evolution is defined by some equation. And so in this small schematic, each of these little gray circles would represent a neuron with a state. One set of things I think about are dynamical systems in biological settings, right? So in this case, a state might be the voltage of a neuron or a population of neurons. The parameters might be the synaptic strength of connection between the neurons. And this gives us, in biological systems, very complex patterns, spatiotemporal patterns of activity that produce lots of interesting behaviors and internal models. We can also think about the artificial side of things, where each of these nodes would just be the activity of a neuron, some real number perhaps, and the parameters might just be the weights between those neurons. And these artificial neural systems can do quite miraculous things. For example, here is a source separation problem for mixed signals. And so here's some time trajectory in R3, which is a linear sum of two very pretty looking time series on the right. And what this neural network has been trained to do is that it's been trained to separate this mixed signal through some means, right? And in both of these examples, in biological or artificial systems, it's the connectivity that largely defines these changes in state over time. And what I'm typically interested in is understanding exactly what the role is between the connectivity and the types of changes in state that we want. So in biological systems, an important question is what patterns of network structure are important for controlling activity, right? This may be for therapeutic interventions using some kind of electrical or drug-based stimulation. But in recent work, what we can do is we can decompose the individual edge weights of biological neural systems, and we can represent them in geometric space. And I won't go into the details, but some geometric properties of these representations tell us exactly which modes are easiest or most difficult to push the system in based on some subset of control inputs. For artificial systems, generally, a question that I find interesting, albeit from maybe a slightly different perspective, is how does neural connectivity encode and manipulate internal models, right? Ideally, these neural networks are learning something more general and generative about the world, and beyond just different training algorithms and how effective they are, these algorithms typically get us to one set of edge weights or a set of edge weights. And the question is, what about that set is special? Can we somehow understand this incredibly high dimensional parameter space? And in another work, I looked into sort of how can we explicitly tie the connectivity of recurrent neural networks to understand how they represent and generalize information. So on the left panel here, or the middle panel, is a few training examples of time series. They're little spirals that go into the center of each point for two different parameters of a training set of data. And this data are generated using nonlinear equations. And it's, yeah, I'll get more into the specifics of the equations later. But given this small training set, these neural networks can actually modify and manipulate their internal representations of the generative equations for the training set to produce a prediction that's crazy and has never been seen before by the neural network. So with that, I'll go into a bit of the motivation behind this particular project. And it's to get program level computing with neural networks, right? So when we think about computing, we typically think about computers, and computers have some very particular properties, right? Computers go really fast. They can manipulate information on the order of gigahertz, but their processing is fundamentally sequential. Now, I know that there are a lot of ways to get around the sequential part. You can have many different cores. You can run it on a GPU. You can modify your instruction sets and your scheduling to perform lots of computations at once. But at the end of the day, the way that the computer cores and algorithms scale with the dimension of the problem typically tends to be quite poor, right? You always need to read some data from memory. You always need to manipulate that data, and then you need to send it back into memory. And you have to do this more or less sequentially per core. But the way that neural systems compute are very different, right? They're much slower, right? So the firing rate of a neuron caps at about 1 kilohertz, right? And they can go a little faster, but it's 6 orders of magnitude smaller than whatever a computer can produce. But all of their computation in exchange is done in a fundamentally parallel kind of way, right? Every neuron is firing at every point in time. And while there's a lot of evidence that shows that certain brain regions are more responsible for manipulating information than others, at the end of the day, the way information is represented and manipulated is very different, right? And so the question is, can we precisely program neural computers the same way that we do silicon computers? So why might we want to program neural networks? Well, from a machine learning standpoint, for example, we might want to work directly with internal models of neural systems, right? We can train them to learn these complicated models, but maybe we would like to make sure that there's no bias in the models that they're using, or that compensate for some kind of lack in representation of our data. Another reason might be algorithmic guarantees, right? We might have neural networks that do well on the training data and maybe even on our test set, but it'd be really nice to be able to clearly define the boundaries of when this model will work and when it won't. As I mentioned earlier before this recording began, with the increase in interest in neuromorphic hardware, it's increasingly important that we develop compilers for this neuromorphic hardware for the software that we want to write, so that we're able to write more powerful software that runs on this hardware. And maybe we eventually want to decompile trained recurrent neural network models, right? You've trained a model and what has it really learned? Let's peek inside the box. Wouldn't it be nice if we could just look at the connectivity that it spat out and directly decompile that into the functions that it learned? The way that computation and representation is done at a very, very high level in silicon computers is through binary numbers, right? So you typically have some electronic circuit implemented through transistors that represents, a 1 or a 0. You get a bunch of these in a row, and then you put a bunch of them into a column into some giant matrix. And what we can do is we can store elements of, say, a matrix into the rows of this memory block using just binary representations, right? So here's a matrix P, and we can just encode every element of P into some row that's addressed by some value. And we can do the same for another matrix Q. And so if we want to perform some kind of computation on this matrix, we have to do it in some sense sequentially, although I know you can parallelize it. For example, we would take the first elements of P and Q, which correspond to the same matrix block, the top left entry. We can load it into some data store. We can perform some operations on it, and then we can output the results into a new block of memory. And then we can do this for the second element, the third element, the fourth element, all the way down to the 16th element to get the addition of our two matrices. And this general basic idea of computing largely stems from Turing machines, right? And Turing machines are really, really great for understanding generalized computing frameworks. My background is not in computer science, and so if I say anything wrong, then please correct me. But more or less, it's just some memory that's on a tape. There can be many tapes, and there is a processing unit that has some states inside of it, and based on its state and whatever symbol it reads, it can modify the symbol, write a new symbol, change the state that it's in, and this is a very, very general way of thinking about manipulation of information. And so here is a multi-tape Turing machine example from this nice GitHub repository on a simple way to multiply two numbers. In an effort to understand computing in neural systems, a lot of work has been done, or some really cool work has been done on neural implementations of Turing machines, right? And this is really cool stuff, and it's an attempt to implement Turing-based computing in neural systems using, not binary ones and zeros, but real neurons with connectivity that evolve according to dynamical equations, and that's really super cool. But what I'd like to think about today is a fundamentally non-Turing type of computation, right? What I'm going to do is I'm going to try to, mess a little bit with this tape processing unit paradigm and see where we can go. And for that, I'll need to introduce you to some brief intuitions about dynamical systems. And dynamical systems are pretty straightforward, right? They're just equations that define what your next state is going to be based on your current state. And so when I write x1 dot and x2 dot, these just represent the time derivatives of x1 and x2. And here is just some nonlinear equation for how x1 and x2 evolve forward in time based on their current state. And so if we were to go ahead and take every point in R2 and then plot x1 dot and x2 dot, we get this vector field. And here's a particular trajectory and a time series from some initial condition along that trajectory, right? Now, nonlinear equations are difficult to analyze for various reasons. And so one trick that we have in our handy toolkit to study these systems is to linearize them, right? And so we can linearize nonlinear dynamical systems about some operating point or trajectory, and that gives us a simpler set of equations, right? And the very nice thing about the simple set of equations is that they can be written in as a linear ordinary differential equation in matrix and vectored form. And the algebra of linear systems allows us to much more powerfully manipulate and understand these equations. And so here is a linearized vector field and the trajectory through the linearized vector field. And you'll notice that in some certain circumstances, the vector field is not so different than the nonlinear one, at least locally about the linearized point, right? And so this is going to be a big assumption and a tool that we will use in order to understand our neural networks. And finally, we can have much more complicated trajectories than the ones that I showed you before. So here is a dynamical system of 3 variables and 3 equations, right? And this is commonly referred to as the Lorentz attractor or the Lorentz system. And something that you'll notice about this system is that it has no home, right? It doesn't ever settle into one point. The trajectory doesn't reach some stable fixed point, but rather evolves chaotically over time, right? That's one of the things that strikes me as very beautiful about dynamical systems is just how complex they can get, even at a small number of variables like 3. And this concept of attractor is going to be very important. And there are lots of very formal definitions of this word attractor, but more or less you can just think of it as a manifold that is, smaller than the dimension of wherever you're embedded in, that you just evolve in. Yep.
Sorry,
yeah, go ahead.
So this chaotic looking system is actually moving on a single manifold inside the 3-dimensional space?
Yep.
Okay.
And a fun fact about this manifold, if you think about 3-dimensional space, you can have a point, 0 dimensions. You can have a line, that's 1 dimension. You can have a plane, that's 2 dimensions. The dimension of the manifold that is that this Lorentz system occupies is actually fractional dimensional, right? It's not an integer. And so once you get into chaotic systems, you hit some very interesting geometric properties. Yeah. I am by no means an expert in the intense study of attractors and dimensionalities. Yes. So I'll talk first about state neural programming languages, and this is programming using the neural network's state, and this is going to have 3 easy steps. The first step is to understand how the inputs into our neural network are represented in the neural states. The second is going to be the output representation, which is how can we use the representation in the neurons to give us a particular output that we want. And finally, the magic is going to happen by performing feedback and setting the outputs back as inputs, right? So you can already see that a little bit of what I'm going to talk about is less about the specific, any kind of specific image or time series that we're showing the network, and more about what I'm going to call symbolic representation that the neurons have of inputs as we treat the inputs like variables. So we'll get a little bit into that, right?
Can I stop you for a moment? Sorry.
Yeah.
Is it just the network feeding back into itself, or is that also external input?
Just the feedback, just the inputs feeding back into itself. Okay. I've left this little knob here at the bottom left colored because we'll use it sometimes, but it's not the big idea. The big idea is just that we assume we have some inputs and they are represented in the neural states in some way. And using that representation, we can get some kind of output. And then by feeding the outputs back as inputs, what that effectively translates to is changing the connectivity of the neural network in such a way that those symbolic output representations are equivalent or set equal to the symbolic input representations. And that means that this neural network, through this feedback, is able to solve some algorithms. Yeah.
So in a sense, the input is fed prior to the initiation of the network.
Yes, 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 yes.
And then it evolves on itself in order to eventually generate an output.
Yes, 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 yes.
Okay.
So steps 1 and 2 are actually just theoretical steps. They're not simulation steps. They're just steps that are needed to figure out what kind of feedback we need. And once we do that, then we start running the network, and it runs some algorithm.
Okay.
So let's start with the input representation. Throughout, I'm going to be referring to the recurrent neural network as a reservoir, because reservoir computing is sort of where these ideas are most simply and prominently studied. So by reservoir, I just mean the neural network, right? And the equations that govern the evolution of a reservoir can more or less be written like this. So here, R is some n-dimensional vector of the state of the reservoir. These are just real numbers. X is whatever inputs we provide. C is a control parameter that we use, maybe every once in a while. And D is some bias term that we can also pick, right? And so when we're talking about the representation of the reservoir, what I'd like to do is I'd like to write the state of the neurons R as a function of my inputs X, right? From a language modeling sequence theory perspective, maybe X is the particular corpus of text that you are feeding into your neural network, and R is just the activity of the neurons. And all I'd like to do is given some sequence of information, I would like to know what the neural states are going to be, right? Just in continuous time. Okay, so representations in computers are done using binary numerals, right? But if we want to get them in neural systems, then we're going to represent the inputs as continuous symbols, right? And so in our quest to write the reservoir states R as a function of our inputs X, that's generally difficult to do for some nonlinear function G, like a hyperbolic tangent. So we're going to linearize the dynamics about a point, and that's going to give us a linear dynamical system. And so just like before in the two-state example, we have the time evolution of the neural system that's equal to some matrix times its state plus some input, right? And so once we have it in this linear form, the next step we can do is to perform a convolution, right? And this convolution is just integrating the dynamical system forward in time. And because the system's linear, it takes this nice form. And so we can write R of t as a function of x of t, which is exactly what we wanted, and the connectivity. However, there's an integral here, which makes life kind of difficult. And so the third thing we're going to do is we're going to perform some Taylor series expansions in states and in time in order to write R of t as weighted sum of polynomials of the inputs, the time history of the inputs, and so on and so forth. And so you don't have to follow through this derivation exactly, but at the end of the day, the important thing is that we are going to be able to write the neural states at any point in time, given the state of the input and its time history. Does that make any sense? Does anyone have any questions about that? Yay, nay, no good? I think you're muted.
Seems like we're gonna keep going because no one's
Okay.
raised a hand. So this
Awesome.
input is coming in continuously.
Yes, the inputs are continuous. So X is going to be some time series. Yep. Okay. And
is
so,
this X eventually going to be the feedback of the network, the output of the network, or it's a separate input?
Sometimes it's going to be the output, right? So
I
you can
see.
imagine in a very simple case where if this is the input x,
Mhm.
and then we write an output that is also x, and then we perform feedback,
Mhm.
then that lets us store a memory inside our system, right? The neural states are going to project an output that will translate back to the same input, and then we'll be able to store some pretty interesting memories that way. Some other times you can imagine that we program our outputs to be some function of the inputs, right? And that's going to set x equal to f of x
Yes.
when we do the feedback, and then it will solve an algorithm, any algorithm that you can define using x is equal to f of x, right? So that's the general idea. Excellent question. For this representation step, basically, beyond any of the derivations, the big thing you need to know is we are able to write the neural states as a weighted sum of inputs, cross terms, and time histories of the inputs, no matter what these inputs may be, right? So given some time series, right, I can first compute all of these terms, and then I can tell you approximately what the neural states are going to be without ever having to have simulated the neural network, if that makes sense, right? So this is the first step of our programming language. So the second step now is to use the representation of these neurons in order to, get some kind of output that we want, right? So using our symbolic representational basis, which are just the weights preceding the polynomial terms of the inputs, we can go ahead and we can just solve a linear problem in order to get a particular output that we want. Right, so I'll go through this again, right? R of t, or the reservoir neural states, can be represented as some weighted sum of inputs and nonlinear terms of the inputs, right? And then we can just take linear combinations, weighted sums of the neural states, in order to give us whatever function of the inputs that we want, right? So using all of these terms, if we want to rotate our input along the z-axis, or the third dimension, then we just need the first output to be a weighted sum of these representations, such that you have minus x2 here, and then the second output to be a weighted sum to give us positive x1 here, and then x3 maps to x3. And when we do this programming through this matrix W that encodes all of our linear mappings, when we drive our recurrent neural network with some complex time series, this input signal, the rotated output is going to actually match the true rotation quite well, right? And so, this might be a bit of a simple example, but the reason why I'm going through it so slowly is that it's a little different, I think, than how people typically think about training neural networks, right? I didn't show it the data first, right? I never told the neural network what x is going to be. Instead, I said, for any x and time history of x, rotate it about the third axis. And then when I drove it with some time series, it did the true rotation, right? So does this make sense?
We'll see if someone asks. But you are getting one question.
I'm having difficulty hearing.
Can you hear me?
Is anyone else having this problem?
She said that there's a question in the chat for you.
Can you hear me?
A little bit. Maybe my audio is off.
Maybe someone else can read out the question.
Can you hear me?
Yeah, I can.
Okay. She said that there's a also, yeah, I can hear you quite well, Gail, by the way. But
okay, then just
she said that there's a message in the chat. Is M0 somehow equivalent to a random initialization?
M0, M0.
Like in this symbolic representational basis.
So in this symbolic representational basis, M0 is just a offset term, right? That's largely set just by the bias term of the neural network. So if you think about the equations, if x is 0 and d is 0, so there's no bias term and there's no inputs, right? Then 0, the neural states are just going to go to 0, right? And so that's kind of the same thing for the symbolic representational basis. This is just a constant, or it's a constant vector that's just there to serve as an offset. And you raise an interesting point, which is that in this system, I'm going to randomly initialize A, B, C, and D, right? So the only thing that's ever trained is W, if that makes sense. Yep. So M0, M1, M2, all of these are just going to be, very complicated functions of the initial parameters that we started with, A, B, C, and D. And these are randomly initialized. Yep. Okay.
Cool. Thank you.
Awesome.
There's
so
one more question. You randomly
yeah.
initialize them and then keep them constant.
Yep.
Is that
Sweet. Cool. So let's move on to some actual computations, right? So rather than just rotating a signal, let's say I give my neural network two inputs, P and Q, and I want them to perform some matrix operation on them, right? So let's say P is a 4x4 matrix and Q is a 4x4 matrix, and O is a 4x4 matrix, and we want O to be some function of P and Q. If we want it to be a element-wise addition of matrices, right? Then we just have to make sure that these linear combinations of representations give us a 1 in the Pij column and a 1 in the Qij column, right? So basically we want the output, the ijth entry of the output to be 1 Pij plus 1 Qij, right? If we want a subtraction, then we want 1 Pij and -1 Qij. For an element-wise multiplication, we want to actually now start taking advantage of the quadratic terms in the representation, right? You have not just linear terms in the inputs, but you've got x squared, x cubed, so on and so forth. And so we want Pij, Qij to be 1. And if we want a matrix multiplication, then we want Pik, Qkj, where k goes from 1 to 4, to be equal to 1, right? And so when we program our output matrix W to give us these outputs, and then we drive our neural network with two randomly initialized matrices P and Q, the output indeed matches P plus Q, P minus Q, P element-wise multiplication Q, and then P matrix multiplication Q. So that is going to be kind of, for the state neural programming language, the big fundamental idea, right? You have the representations, right, of the inputs in the neural states, and then you use linear combinations of the neural states in order to give you an output function of the inputs that you want, right? And that output function can be, algebraic, it can be nonlinear, it can be whatever, yeah. And so the final thing we're going to do is we're going to.
Sorry, there was a question in chat again about these values, I guess. So the question was, are these values in M2, etc.? So these rows that you're showing in the top right corner, these are different elements of M2 on this slide, right? Or M3, depending on which term you're using here.
Yes, you can think of it as WM3, right? So it's not just M3, because M3 or whatever it may be would be n-dimensional. It would be an M by something matrix where that something is all of the quadratic cross terms, right? X squared terms. That's held by every neuron. And what we're going to do is we're going to project that representation from n dimensions into 1 dimensions, or in this case, 16 dimensions, right? Where each one of those is going to be some Pik, Qkj for each I and each j, if that makes sense, right? So exactly as you said, for these additions and subtractions, we would have to project the M1 terms, right? Because M1 is the neural network's representation of the linear terms in X, right? But it's not just enough that we project M1, right? We also have to project out the terms we don't want. You know, we have the constant term, we have the quadratic terms, cubic terms, so on and so forth. So that W matrix, when we do the training, needs to not only project M1 to Pij, Qij, but it also needs to, you know, cast everything else into the null space, if that makes sense, right? And same for this matrix multiplication, Pik, Qkj, it needs to map to 1, and all of the linear terms, constant terms, and other quadratic terms, it needs to map those to 0, right? But the trick here is we're turning that into a linear problem as opposed to a nonlinear quadratic problem. So excellent question. Maybe I can pull up the chat. Yeah, okay, awesome. I'll keep this tab handy. Cool. So now what we want to do is, instead of just having functions of the inputs to give us some output, we want to have our neural network solve some problems, right? Solve some algorithms. And what we're going to do is we're going to feed the outputs back into the inputs. And what that's going to do is it's going to set whatever output function we have equivalent to the input variables X, and thereby the evolution of the neural network will converge to the solution of that equivalence relation. So I'll give you a simple example. And I'll be using something called a neural processing unit. This is just a fun name that I liked. But all it does is it takes a matrix and 2 vectors and it outputs mx plus b, right? So pretty straightforward. And if we have several of these neural processing units and we chain them together, then we can have our output function be defined as some complicated vector equation, matrix equation. And this particular equation defines the gradient of a least squares problem, right? So given M and given B, it's the least squares solution to the variable X, right? It's the gradient. And what we'd like to do is we'd like to set the gradient equal to 0. And to do that, all we have to do is project the output, which is this complicated symbolic expression, and feed that output back into the inputs, and that sets an equivalence relationship between the output and the input. If that kind of sort of makes sense. And so what this equation is going to do is it's going to try to set the equation for the gradient of the least squares norm to 0. And so what this feedback looks like is if these are our base neural network equations, where X is the input and WR is the output, right? And we've programmed W such that the output is this complicated expression, then we're just going to set the output equal to X, and then we get feedback, right? So that's how we take, the inputs X, and we replace them with a linear combination of neural states. And that means our new connectivity matrix looks like A plus BW times R, right? If that makes sense. Cool. And so if we, randomly initialize some matrix M and some vector B, and then we evolve our neural network according to that matrix M and that vector B, then the output really converges to the solution to the linear equation. This is for a 5x5 system. That's going to be the first part of the programming language using just the states. Does anyone have any questions?
I hope you can hear me well.
Okay, I can now.
So just to clarify, W is a sort of where we come and express the programming, where we express what we want to happen.
Yes.
which is going to somehow are all of the m's derived from w as various derivatives or something like that? Or?
Yes.
Okay.
So if you are familiar with Taylor series expansions, right? It's just coefficients in front of x squared, x cubed, so on and so forth. M is very precisely those coefficients, right? It's just a matrix of those coefficients by taking Taylor series expansions on in vectors. Yep.
And I imagine W must be extremely large but sparse.
So because all W does is map neural states to output states, W is just, in this case, 5 by n.
Wow.
Right.
And then the M are derived to almost arbitrary n.
Yeah, you can derive these coefficients ad nauseum to however many high order terms that you want. But at some point, and this is an interesting thing, based on how you pick your parameters, right? The norm of A and B and D, the expressivity of your neural network to the time history of your states is going to change, right? So if you don't care too much about the time history of your signal and encoding that into your neural states, you can pick a small a and a small b, right? If you pick a large A and a large B, then you're going to be representing a long time history of neural states. And so you can tune the expressivity by tuning the norms of these input matrices. And this is a very interesting way to explicitly explore the expressivity of recurrent neural networks, because how the amount of expressivity comes out is just in a linear way, right, through these coefficients. Yeah.
Thanks.
Cool. So if this is not already a little too esoteric, the big idea is not so complicated, you know. And I'll do a little bit of a recap. So first, all we wrote down how the neural states represent the inputs, and that's just through a sum of weights, weighted sum of, you know, input variables and polynomial terms and time histories. And then we just program some output by taking linear combinations of those representations to give us some function of the inputs based on that representation. And then by performing feedback, we set an equivalence relationship between the outputs and the inputs to solve some kind of x equals f of x kind of equation, right? And so the thing I want to emphasize here is that we're not solving this least squares equation through, you know, some implemented package in Python or MATLAB. We're just evolving forward a recurrent neural network, and that neural network evolves towards the solution to an algorithm that you programmed yourself into this system. Okay. So next, I'll move on to dynamic neural programming language, which is then programming using the neural network's dynamics. And this will be a little more complicated, but at the same time, not very different at all from what we've currently discussed. So in our neural network formulation of the reservoir, there's one term that we've left out, right? And that term is this R dot term. And this R dot term is very important because it defines how the neural network evolves forward in time. Just like how whatever instruction set that you pick determines how a computer is going to evolve forward in time, right? So in our programming language, we would like to specify not just the state of the system, right? We don't just want to program the these kinds of algebraic equations, but we also want to take advantage of the time evolution. And so what we're going to do is we're going to, instead of using R in our programming, we're going to use G, right? So before we had R of t, we wrote out R of t as functions of X, and then we, wrote algorithms that way. Now we're going to replace R with G. And the benefit of doing that is if you rewrite these equations, right, G is going to equal R plus R dot, right? And because it's R plus R dot, that means in our programming, when we, program outputs of G instead of R, we're going to be programming outputs of not just the neural network's representation of states, but also the neural network's representation of its time evolution, right? So rather than saying WR of X is equal to F of X, we're going to say WG of X is WR plus R dot, which is going to be equal to X plus X dot. This is kind of weird. And I think getting into the technical details of this is a bit challenging, but conceptually, it's not too difficult at all, right? All you're doing is instead of now just using the neural states, you're also telling where you want the neural time derivatives to go, right? You're not just telling where you want the states of the neural network to map, but you're also telling where you want the time derivatives of the neural evolution to map, right? And so because we have the ability to program into our neural network, not just X, but also X dot, that means we can define both the state and the evolution of the state in our programming. And so one such way to do this is to, okay, this is complicated. I'm just checking the time here, which is almost noon. But yes, I told you about dynamical systems earlier, right? And what this lets us do is it lets us program not just fixed points as memories, but dynamical attractors as memories. And I will just very quickly go through all of these slides because I'm running out of time. But yeah, the short story is by using G instead of R, we can define a feedback that embeds these very beautiful looking dynamical attractors as memories inside of our neural network. Yeah, and so a fun game that we can play is if we can program dynamical systems inside of our neural networks, and our neural network is a dynamical system, we can program a neural network inside of a neural network. So we can do some kind of software virtualization of neural networks, right? So if we have a Lorentz attractor, which is a dynamical system that we've programmed into a neural network, then we can write out the code for the dynamics of this first neural network and embed it into a second neural network, because all this is a dynamical system. And so if we evolve the big dynamical system, then it simulates the evolution of the small neural network, which is then simulating this memory and state space. So you can do all sorts of things with this. I definitely don't have time to get into it, but you can program in logic circuits based on dynamical systems properties, which lets you create neural implementations of binary adders, of persistent memory, of these multi-vibrator oscillator circuits. Yeah. So for this dynamic NLP, I think the big conceptual takeaway is you can not only program in static representations, outputs that are functions of X, but it allows you to program in dynamic information as well, right? So you can also program in specifically how you want X to evolve, the representation to evolve, right? And what this means is that as long as you can write out any program, anything that you want to solve or evolve, or any algorithm as a dynamical system, right? If you can write something as X dot is equal to F of X, then you can program it into a neural network through this programming language, and that neural network will simulate that algorithm for you. So yeah, this is my PI. These are all of the lovely people who have provided me with great comments on this paper. So I guess with that I'll end. Thanks for listening.
Thank you. I'm going to stop recording, so unless people have questions that they want to ask in front of everyone for YouTube forever. And if not, then I'll stop recording and we'll have the more informal chat. Have a few seconds.
It sounds like the last thing that you talked about is like basically this neural computing equivalent of a universal Turing machine where like you can emulate any.
Yep.
Pretty sweet.
Yeah.
Wow.
And so at the beginning of this talk, I talked about like different systems are good at manipulating information in their own native language, right? And the thing I'm trying to push, at least in this particular project, is that one of the native languages for recurrent neural networks is dynamical systems, right? It's just quite literally time evolving things. And so more than computers, neural networks are definitely better at solving those kinds of problems. And this is just a programming language and a compiler to tell you how to translate any of those problems that you have into a simple continuous time element network or something. Yeah.
I have one more question, if you don't mind. So this requires kind of like continuous inputs, like continuous time. In NLP, I mean, just because this is the purpose of our Discord channel, things are often discrete. I mean, things are always discrete in some way. I'm curious, like, is there, or does anybody else, like, what could be an NLP problem that would fit nicely into this framework? Like maybe something with speech, or I'm just curious kind of what people think about that.
I could add a little bit there in that this is only derived for continuous time systems because that's what I started with. I don't think it'd be too difficult to actually extend it to discrete time systems. I don't think it would be too difficult at all, especially because most of this framework relies on linearizations. There are very explicit mappings from linear continuous time systems to linear discrete time systems, right? So through those mappings, it should be pretty straightforward to derive an equivalent framework for discrete time.
Cool, thanks. And thanks so much for your talk.
I have a weird question. Is there a way that you could make the connection for me for how this simulation of Pong would look if we were looking at a real biological system, for example? What would this mean? Has the simulation been given sort of the constraints of how the ball bounces around, and I assume the paddle moves constantly? And then the biological system would be constantly outputting the next step?
I see. So I will try my best to answer these questions. So in the game of Pong, right? The way that contact detection with the wall, contact detection with the paddle, these kinds of things are implemented aren't through if statements. They're done, and then the movement of the ball, so on and so forth, they're all done through dynamical equations, right? So we can actually write this entire game of Pong as x dot is equal to f of x, you know? And what that looks like at the neuron level is this, right? This is really what the recurrent neural network is doing as this ball is bouncing around. And all we've done is we've embedded those dynamical equations into the connectivity of the system, right? And so for a biological neural network, you can, for example, close your eyes and play games of Tetris in your head. If you've ever played Tetris for a long time, then it's really easy to visualize the falling blocks. How neural systems learn to do those simulations and visualizations is I don't have the answer to that, but this is one way that you can get that level of, specificity of neural imagination into the connectivity. So, the neural network in biological systems won't look like this, but this is, if they did look like this and they evolved very simply, then it would be the same thing, and that's why one of the future directions of this work is, to look at trained neural network models and use this programming language to write a decompiler, right? Can we then now look at a biological neural system or an artificial one that's learned to visualize something, and back calculate the models, the dynamical models that they're using to do that. So
eventually
I don't know.
Decompile a brain.
Yeah, and that sounds kind of crazy, right? And maybe it sounds crazy when you think about it from the perspective of, oh, decompile it into a bunch of if statements and or statements and logic gates, and that sounds hard, right? But it might be the case that the language that the brain is using to learn models and do computations isn't C, right? It might just be x dot equals f of x, right? In which case we need dynamical decompilers. Yeah, that makes sense.
Thanks.
Yep, I hope that answers your question.
It gives me direction. I want to see if anyone wants to ask any more public questions before we stop the recording.
Yeah, I wanted to thank you for a wonderful talk. And on the question of discrete time versions of systems like this, there is the area of population protocols in distributed computing. So there, the original model was a bunch of basically identical finite state machines that might be in different initial states. And you have this whole population of them interacting. And there are rules for when they bounce against each other pairwise, how their states get updated. And the analysis of these systems turned out to be useful to think in terms of essentially discrete time dynamical systems. So it might be interesting to look at that stuff. I did some work on it with Jim Osmus and Mike Fisher. And we ended up, in fact, simulating computers with these things. So it was a little reminiscent.
Could you tell me the search term again? I didn't.
Population protocols here. I can give you a link to Jim's. There's been more work, but there's a survey of Jim's. Let me see if I can find it here.
Because that sounds really cool.
Yeah, it's a lot of fun. It turns out that biology got there first. So
usually does.
Yeah, absolutely. Let me drop the link in the chat. I can do that. So this is Jim's survey. It'll give you a sense of it. And there's been a lot of more work that I haven't followed since. But it turns out that we came up with this three-state protocol for deciding majority. It ends up having actually been implemented in the cell. When a cell decides to divide, you don't want part of it thinking it's dividing and the other part not thinking it's dividing. So there's a biological mechanism that allows basically all of the cell to decide whether it's dividing at this point. And the biologists understand it pretty well. And it turns out that it looks like basically a 7-state version of our 3-state, because of the biology, our 3-state population protocol for majority, which I thought was just classic, that, evolution was long since there. It's great.
That's really cool. Thanks for sharing.
Sure. And thanks for the talk again.